So thank you very much. So this is the last paper of today. Everyone is very tired. I mean, or maybe not. I mean, but I mean, this paper is going to be kind of strange, essentially because the paper doesn't exist. That makes it virtual, and this is entirely work in progress. Here, I will put it like that. So this is John Ward with. I should have started like that. This is John Ward with Ricardo and with Samuel. And the usual disclaimers apply, even I doubt that my employers have any concern about it.
What's your name?
Sorry? Oh, DSE. Oh, so yeah. No, but that means that there are several issues here that have not been covered. Anyway, that makes it so Ricardo is at PSE, not Sciences Po. But anyway.
Your name is what?
Sorry?
Your name is what? Which one of you?
Okay, so my name is the one in the middle.
Okay.
Galo Nuno. Ricardo is one of the co-authors. He's now at the PSE, Paris School of Economics. He used to be at UCL. And Samuel is a colleague from Banco de España. So the point of this, I mean, this is a paper in the middle. So I was given the opportunity by Simon to present it here. So I'm very much looking, I mean, this is honestly, I am very much looking for your comments because, I mean, the paper is very fluid at this moment. So it can change, I mean, in a matter of weeks. Also, I mean, we have kind of two presentations, the economic presentation and the technical presentation. And this is the technical presentation. So everyone who is looking for deep economics issues, I mean, so can already go and prepare for the dinner. So, and it's nice because in a way the paper is going to make a counterpoint to Jonathan's presentation, because I'm going to talk a little bit about a problem that I find particularly interesting, but I'm going to give you kind of a poor man's solution that is going to be much simpler than some of the alternatives that have been presented. Okay, so the problem that we want to deal is about asset pricing. So, does marketing completeness affect asset pricing? So, I mean, we know, I mean, let's take the basic Lucas tree model. So you have a tree, given you this fruit. I mean, this is the dividend. You want to put a price to the asset, and then markets are complete. So essentially, I mean, you have that the price of the asset is just the discounted sum of future dividends discounted using the stochastic discount rate that is based on the consumption of the representative agent. The question is, if you move from market completeness to market incompleteness, does it matter? And there is a paper published in the Journal of Economic Theory by Kruger and Hanno Lustig that says no, under certain conditions, you can move to this kind of Ajagari-Bewley environment, and it doesn't matter. It is not relevant for the pricing. However, what happens if you deviate from this kind of restrictive set of assumptions? Like you can move to this kind of borrowing limit that should be proportional to income, and you need to have particular preferences, and you need to have. It's relatively. I don't want. The paper is great, and the conditions are relatively wide. But still, it's not very difficult to find situations in which they are going to be violated. So there are a number of recent papers that have analyzed how asset prices affect heterogeneity. But now the question is, what happens when also heterogeneity affects asset prices, which in turn affect heterogeneity? So you have the fourth circle. So can we do asset pricing in heterogeneous agent model? And then the question is, that 95% of the papers in heterogeneous agents deal with local solutions, some kind of perturbation solution. It can be MIT shocks in the sequence space. It can be by dimensionality reduction. There are all kind of super cool, amazing systems. Here we have, we have a whole plethora of ways to solve very quick, very cool method to solve that. But then, if you really want to solve heterogeneous agent model, Using global solution, then the space of methods is much reduced. So you have, in this room, there are in discrete time some of the people who have pioneered this method. So there are the method by Lydia, the method by Simon, who are both and for instance the method by there are 3 people more. I know there are more people with methods, but essentially they are all. As Jonathan explained, the general idea of this method is typically that you go all in. So you go with the full dimensionality. So you either gonna approximate the whole density, or you are gonna approximate a large number of agents, and then you are gonna solve a large dimensionality problem when you deal with because the problem of solving heterogeneous, globally, this kind of problems is that the distribution, I still have started like that. The problem of this is that the density is an infinite dimensional stochastic object. So then when you have to solve the dynamic programming problem of the atomistic guys, you need to introduce you need to take the derivative of the value function with respect to the density, which is changing stochastically with time. And this is the master equation that Jonathan was presenting before, okay? So then one way is to try to approximate this master equation in this kind of brute force ways, high dimensionality, and then use deep learning to do that. But then there is another kind of poor man's method that probably is closer to what actual human beings do in reality, which is the basic Russell-Smith method. So the idea, and I stopped to Per while we were away, and he has granted me permission to talk about the Russell. so let's keep that settled for the moment, okay? So I have we can call him afterwards, and he will confirm my words.
Are you doing continuous time?
I'm doing continuous time. I'm doing this is why I call. In order to avoid any problem, I called him and said, "Look, Per, can I use this?" And he said, "Yeah, you can." So let's leave that settled for the moment. So then the issue is the basic idea is that the point of the plain vanilla Russell-Smith methodology was to do this kind of projection over a simple set of let's call them moments, which of variables that summarize the dynamics. We could call them probably more properly components that summarize the dynamics of the distribution. And typically, again, in 99% of the papers, is a mean of the distribution. But this is not always useful. And the point is that the typical, this issue is that, of course, this is a very radical dimensionality reduction. But in most models, it works, and it works because you have this approximate aggregation in which individual policy functions are typically very much linear with respect to the endogenous state, and then when you aggregate, it is not much of a problem doing that. But the Russell-Smith methodology has 2 assumptions. One is that, but the second one is that the aggregate law of motion, you have to plug it in. So in the Russell-Smith methodology and in the basic Russell-Smith model, you say, look, I'm going to impose that the aggregate dynamics of aggregate capital, which is the mean, follows a log linear. Log linear on aggregate capital. And then it can be fully nonlinear on the exogenous state. And it works because the basic neoclassical model with incomplete markets is pretty linear at the aggregate level. So at the end of the day, you don't need to use this kind of method because you can do it by perturbation. But then what happens if the underlying model is very nonlinear? So then if the underlying model is very nonlinear, you need to find some kind of universal approximator that describes the law of motion, what we call the perceived law of motion of this moment, and that is flexible enough. That can be a neural network, that can be Chebyshev polynomials, that could be anything. But then not everything works in the same way because there are extrapolation problems and there are other issues about how to do it. So in a previous paper with Jesus and Samuel, what we did was just to illustrate how you could deal with this kind of nonlinear problems at the aggregate level in which quasi-aggregation still holds just by using a neural network. And then with a neural network, and it doesn't matter if it's continuous time or discrete time. This is totally irrelevant about the time. This is about you can't go through the Krasel-Smith way, but in situation in which the dynamics are not linear, because going, again, I will repeat it. If the aggregate law of motion, if aggregate dynamics are approximately linear, use perturbation. But if aggregate dynamics are non-linear, either you go all in and you really deal with 1,000 guys or 1,000 beams of the histogram moving non-linearly, or there is this kind of midway, which is this one, which is use Krasel-Smith, but you cannot literally use Krasel-Smith as some papers do in the same. But by that, what I mean is that what you can, if the law of motion is linear, then you can plug a linear law of motion and that's it. But if it is non-linear, and then I'm gonna kind of bring my deep Tolstoy, every linear model is alike, but every non-linear model is non-linear in its totally different way. So then you cannot say, okay, what if this is non-linear with a quadratic form here and a cubic there? This is shit. You really need to have some kind of universal approximator that is able to map any kind of non-linearity, because the non-linearity that you find, I will show you later, the kind of non-linearity that you have cannot be described by concave function and x squared. They are super strange things, like what I do when I take a blanket and I put it over a leg. Yes, there are several questions. Let me.
Just want to say a small defense for because we're not assuming that it's overall linear, we're just assuming that the condition on the shock, the forecasting function for capital is not linear, right?
Exactly.
So even in the standard Lausanne-Smith, it can be very non-linear in the shock.
No, that's totally right. So in the plane manila, and now we connect with the issue. In the plane, in the original, in the true, God forgive me for using the word, in the true canonical Krasel-Smith, with discrete value of the shock, you run a log linear regression for each level of the shock, so it can be super non-linear over the exogenous shock. I'm with you. Tell me.
In the Great Depression, stock prices.
A question that started within the Great Depression.
Prices fell by 89%. In heterogeneous agent models, the distribution of wealth matters a lot. If you have a shock of 89% to stock prices, you have made a massive change in the distribution of wealth. And any model that will not accommodate a massive change in the distribution of wealth like that is not properly a heterogeneous agent model. That's my point.
That's a very good point, and this is the kind of question that we want to explore with that.
Good.
So this is precisely the issue. The issue is that when you talk about asset pricing, there are these large movements that produce large changes in the distribution of wealth, and then also, Ricardo, who is the one who has, is the smart one in the team, he has this point that in order to understand asset prices, you really need to understand wealth inequality of the top 1% or 0.1% or 0.01%, because those are really the guys who.
No.
I don't know.
No, that is not right. If the stock market falls by 90%, then the people who were in the top 1% are now poor. The portfolio choice of a poor person is different from the portfolio choice of a rich person.
Exactly. That's true.
So it is not, yes, there will still be a top 1%, but they will be poor now instead of rich. So you need the portfolio choice to be contingent on the level of wealth. And if you radically change the distribution of wealth, you will radically change portfolio behavior, full stop.
Exactly. So I don't know why you said no, because that's the whole point. So
no, you said it all depends on the top 1%.
No. But that's exactly. But this is endogenous, and it's true that in general in the data, the portfolio, and that that would I would need half an hour to talk about that. But the portfolio, models have hard times at replicating the kind of portfolio rules that are found in the data. But that's for another day. So I just wanted to talk today a little bit about techniques, but I mean, later we can discuss more about these issues, which are the important. So first, I'm just going to start with the plain vanilla representative agent case in continuous time. So essentially, what we are going to have is this unit of a tree with a dividend, and the dividend is going to follow some diffusion process. Can be an Ornstein-Uhlenbeck, can be an AR1, can be a random walk, can be whatever you want. This is totally irrelevant. And then it trades at the price Q. So I'm even glad because I'm using, I think, the same notation as Jonathan, so it will be even simpler to follow. And then what we are going to have is a representative agent, and the representative agent, he just, derives utility from consumption and faces some budget constraint. And then K here is the number of pieces of paper. So I have this number of pieces of paper, and depending on the number of pieces of paper, they entitle me to receive these dividends. So why? I collect a fixed endowment set, capital set, and then essentially what I have to decide is how many pieces of paper I want to have in the next period, so in continuous time. What is the rate of change of the number of pieces of paper that I have, multiplied by the price of pieces of paper, okay? And then in equilibrium, the total amount of pieces of paper is fixed, is equal to 1. So then we come to the problem of non-trivial market clearing condition, because this is not a Nayagari kind problem. This is a Haggett kind problem. This is not that I'm gonna have to clear the market in a much more convoluted way in this model, point by point, okay? And then this is the aggregate market clearing condition. And then if you do some cool mathematics with those lemmas and so on, but you reach that equation here. But before reaching that equation, just let me make some particular point. In this model, the only state variable is the dividends. So then, given the dividends in any point in time, the representative agent knows the price. So there is a one-to-one mapping from dividend to price. You tell me the dividend, I tell you the price. Okay? So essentially, what the representative consumer has to solve is just this kind of simple Hamilton-Jacobi-Bellman equation. And then by operating a little bit over that, you get the standard issue the standard equation that the price of the asset today is just the discounted flow of dividends using the consumption. And then you can, consumption is just the dividend plus the endowment. So that is the price. So essentially, given, yes?
If uncertainty changes, the general theory in Keynes said uncertainty is the key driver of business cycles. I want a leap in uncertainty. I want there to be a jump process for sigma. That's what Keynes said was key.
Jump process. Yeah, that I can give you. So, if you refer me for a top 5 and you tell me that, I give you. That I also. I don't know if this is being recorded, but I want to make that. If you are the referee and you ask me for that, I will do it. I will do it.
I'm not.
I can do it, and that doesn't make any particular. So that I can deliver. But I agree. I don't know if I agree, but I know that I can do it. So that's one of the things. So now let's move to incomplete markets. So now, what is the main change when you move from representative to heterogeneous? That I move from capital letters to small. That's the most important. So essentially now, what we'll have is a continuum of agents. And the only difference is that now, what I have replaced is so each of these agents, now they're indexed by I. So we'll have this small a. So a small a is the amount of pieces of paper that you can have. And we assume that, that you cannot have negative pieces of paper. So you cannot short the asset. The asset cannot be sorted. So you always have to have pieces of paper. I cannot have a negative piece of paper. And then income follows a Poisson process, a two-state Poisson process. You can be employed and unemployed with exogenous probability that here are unrelated to the stock market, okay? And that's it. This is a very simple model. At the end of the presentation, I will talk about the model that we are really building, in which you have multiple assets and you can have more complicated process for income and so on. But this is a very simple thing. Then the issue here is that the density is given by a Kolmogorov-Forward equation. I mean, given by that, no major issue. And then the problem is now, as I said before, that the price of the asset in this economy depends on the dividend and on the endogenous income wealth distribution. So those are now, so before, with the representative agent, there was only one state variable. But now we have two state variables, but one is a distribution. So then again, using Jonathan's method, I can go all in and just approximate that using a neural network for Q, and then put it in the Hamilton-Jacobi-Bellman equation, in which I approximate for the whole density and solve it. But I mean, in our case, it's gonna be much simpler. So for those of you who are doing a PhD, maybe this is a way that you want to follow as a first ortograph. So here is the master equation, and then the problem, as before, is that in the master equation you have this red part in which you have the functional derivative of the value function with respect to the density, and how can you solve it? So here is here is where Krasel and Smith, God bless their name, come with a super simple solution, which is probably closer to what happens in the real world, which is that people, in reality, I don't know, we are in Switzerland. In Switzerland, I live in front of a bank that is called, I live in Basel, that is called Safra Safarin. Have you ever heard of the bank Safra Safarin? Have a look to the bank Safra Safarin. This is full of traders and bankers. So, I'm sure that if you go to the street, you can talk to a trader and ask them, are you into the business of trading? If they tell you yes, that when you have to forecast asset prices, how do you do? What variable do you use to forecast asset prices? Dividends and prices, or dividends and income wealth distribution in the United States? And I cannot tell it for sure. But I can tell you that with a 95% of probability, they are going to tell you that they use dividends and prices, and not the income wealth distribution.
They don't have any incentives.
That's also true.
Purcell and Smith had labor income. You don't have labor income? Purcell and Smith had labor income was extremely important.
Yeah, we have this. So let's forget about Krasel and Smith. This is so. Let's talk about Haggett. Let's talk about labor income. Okay, so we do have labor income. So labor income is the endowment. This is labor. This set there.
It's an endowment.
Yeah. The endowment is labor income. It's like in Haggett. Okay. This is the same. That's where the exogenous idiosyncratic uncertainty comes from.
That's fine.
No, but thank you for
endowment.
Right.
And there is an asset other than the.
No, in this version, no. In the one that we have coded, that I will talk at the end, yes.
Capital. Purcell and Smith had capital.
Yes, but
Haggett had capital. Okay.
No.
He didn't have capital. So now it's a Haggett model, not
exactly.
Okay, it's a Haggett.
It's a stochastic Haggett model.
It's a stochastic Haggett model. Okay, it's not Purcell and Smith.
No. But
okay.
I've talked about Krasel and Smith methodology, not model. I'm very precise with the words. Okay. My wife is a lawyer, so I know about that.
And your co-authors, which are
my co-author is a lawyer, so I'm surrounded by them, and they studied in the same university, so they have the same.
What do you mean? There's labor income and an endowment economy, and the endowment economy. Okay, there. Oh, I see. The endowment is the dividend.
No, there are two. There is a fixed endowment. It's fixed at the aggregate level, but idiosyncratic at the individual level. And then there is a stochastic endowment. There are two endowments. And the other is not an endowment; it's an asset that you trade. It's a Lucas tree. You got
a Lucas asset tree, and you have labor income.
And look, you have labor income if you want.
And you can trade back and forth, and some kind of and you can sell your labor income for the buying a tree.
You can sell your labor income. Yeah, if you want to, it's an endowment.
Yeah. Okay. So there's an exchange rate. There's the price of shares in terms of labor.
Exactly. Okay. So exactly, that's it. So then the point here is that in order to do the pricing of the asset, what people need to learn is which is the law of motion of the asset prices, and then here in general, people will try to learn that it will have a volatility and a drift that will depend on the prices and the dividend. Yes. Yes.
I missed something in the setup. Why does this price risk not appear in the budget constraint for the lower approach competitive growth?
This because I've written the individual loss motion in terms of price, of pieces of paper. If I write it in terms of money, then I would get the divided by Q, and then I would get the, actually,
Not in real sense.
actually the way that we have coded for multiple assets is that way. So I mean, for one asset you can do it like that, and it's easier.
But you're going to go one asset.
Exactly. When you have two assets, then you have to write it in money wise, and then you have to write it in dollars, and then you have a brief term about the volatility.
Sorry, I might have said that.
Sorry?
I apologize. I might have missed it.
No, but that's a very good. I mean, that's a good point. I mean, because this is just for this particular example. Because I thought, I mean, the other model is more complicated, but I thought that, I mean, given that I would have to present, I would prefer to present the simple than the complicated.
So the labor income is apples, and the stock market is oranges. And they get some apples as an endowment, and they get oranges as an endowment.
Yes.
There's a relative price between apples and oranges.
That is Q. Is the So,
I thought Q was an intertemporal.
no, Q. I mean, Q is the price of the the price of the So you have an endowment. Let's assume that the numerator is the endowment. Okay, you can say that it's labor, so whatever you want, but it's something that can be consumed. So I don't know if you can consume labor, but I mean, like there is a one-to-one transformation because there is a final good, and this final good, there is a total endowment equal to 1, but in every period you can get more or less of that. Okay, and then in addition to that, there is an asset, a Lucas tree, and this Lucas tree pays you a flow of dividends of this unit that you can eat. And then you can trade, that at a price Q. Does that make sense?
You have a flow of labor income, and you have a flow of dividends that are coming.
Yes.
In continuous time.
Exactly.
Okay, and they're independent?
They're independent.
Okay.
They're independent. So then, the point is that, as it will be a surprise to no one, is that we are going to use the neural network to approximate these objects, mu Q and sigma Q. If we are able to do that, then essentially what you have to solve is just a standard Hamilton-Jacobi-Berman equation, only that a little bit, higher dimensional, but it's not, by higher dimensional, 4, not 40 or 400, like 4. Something that you can, something cozy that you can keep under control. So then at the end of the day, the only issue is that you need to approximate those two things. It's a low dimensional. I will insist it again. This is a low dimensional problem. So maybe this is why I'm here kind of by invitation, because this is not high dimensional. But then you can throw tomatoes to me and say, no, but why? You don't need deep learning for that. But our experience is that there are two good set of reasons why neural networks are good for that. One is practical, which is the richness in the computational tools to do it. The second is more theoretical, which is the extrapolation properties. Because the problem here, and that relates to the issue that was raised before, is that for solving the Hamilton-Jacobi-Berman equation here, you need to work in a hypercube. But the problem is that the ergodic distribution is going to be a region of that hypercube. And then the issue is that you need to know how it's going to be the price in every point in the hypercube. But then you don't visit those points outside. But then you need some approximation scheme that doesn't give you totally crazy things outside of the region that you visit in equilibrium, because otherwise, the algorithm will never converge. Okay, so this is why, in that way, neural networks are good at extrapolating outside. Yes?
What's the fundamental reason that you're improving that?
Because it's a way to solve. You can have some kind of adaptive way to solve it. Yeah. But it's the simplest way to do it.
Because I agree it's the simplest to do it, but like fundamentally.
No, fundamentally no. Sorry?
Like fundamentally, you could come up with a way to like enclose the cloud. Or is there a fundamental reason why you have to do it?
No. Fundamentally, there is no reason. So you could do it. Yeah. One point about that, and something that is important to insist about the whole Krasel-Smith problem, is that this is not rational expectation. This is this self-justified concept. So essentially, or similar to what people in game theory call self-consistent equilibrium. So essentially, this is something that on the equilibrium path, so on the region that you visit, the perceived law of motion, so the way that people think that the economy works and the actual law of motion, they coincide on a statistical terms, so people don't make systematic mistakes. But outside of equilibrium, so outside of that region, you don't know. So they can coincide, and then that would be rational expectation, or they maybe don't coincide. And that's the point why extrapolation matters. I mean, because even if there is a small probability that aliens will happen now, I mean, will land here, we need to make an extrapolation about how stock markets will evolve in that situation, because even if it has a very tiny probability, it has some influences on asset prices. So then if the guess made by the approximation method is totally crazy, that will influence asset prices today. Yes?
So the rich people are ones who have been stuck at the high income process for a while, and they're just building up and building up and building
Yes.
up assets. And the poor assets have been stuck at the low income process for a while, and they're
Exactly.
running down and they're running down and they're running down. So the poor people have a high marginal propensity to consume, and they are afraid of the stock market, and they don't want to own stocks, right?
Yes.
And the rich people,
I mean, more that they don't want to own, they don't, I mean, they prefer to consume because they have no other alternative.
It's the concavity of the consumption.
Exactly.
Structure. It's the concavity of the consumption structures at the core of it.
That's the issue.
Okay, so they're going to have very different portfolio choices depending poor or rich.
And I mean, in this case, in the basic model, there is no portfolio choice. I mean, the only portfolio choice is between consume or save. So it's just saving consumption decision, because here I'm not giving them any safe bond. I will give them the safe bond later, but I don't think we will ever reach that point.
Okay, so there's no consumption saving decision.
Yeah. So yeah, there is consumption saving decision.
I'm sorry. There's no.
No, because here there is only one asset. In the two asset model, there is.
Okay.
Okay. So the idea of the algorithm is just, I mean, the idea of the algorithm is just to visit the ergodic, I mean, to propose one perceived law of motion for those two objects, and then just to use it to solve the dynamic programming problem of the agents, then simulate the economy, given aggregate shocks, given this simulation of the economy, you create samples, and given those samples, you train the neural network for the drift and for the volatility. And once that you have that, you feed back those rules to the Hamilton-Jacobi-Bellman equation until you reach this kind of bounded rationality, this self-justified, in which the way that people expect the economy over the simulated path and the way that the economy works over the simulated path coincide. It's as simple as that.
So there are a lot of rich people, they will have low relative risk aversion, and the assets prices will reflect, people are believe in that mostly the economy is a low relative risk aversion.
So what happens, so if you want to know, I mean, I'm not showing it here, but if you want to know in the one asset economy, what happens when you have a negative dividend shock?
Dividends are never negative. You mean just
I mean, that the dividends growth rate. So dividends
are at the low growth rate.
So if dividends were 5, now they are 4%. For temporary. I mean, following an autoregressive.
No, this is the aggregate, because the dividends are aggregate, and
dividends are aggregate. So everyone gets the same dividend. I mean, everyone who holds the asset.
Dividends are aggregate, and idiosyncratic is income. Labor is idiosyncratic.
Exactly. So let's forget about. So what happens if I get a dividend, a negative dividend shock, is that rich people whose income depends mainly on the dividends, they want to smooth consumption and they sell the asset.
They sell the asset
in order to smooth consumption. And then who is gonna buy the asset? Because someone who has then very poor people, they cannot because they don't. I mean, because they are close to the boundary or at the boundary and they won't do it. And then it's employed middle wealth people who purchase the asset from the rich people when dividends, because most of their income still depends on labor, and then they see an opportunity that asset prices are going down, and then I can save a little bit more.
Exactly.
That's the basic dynamics with one asset. Okay, I'm not presenting everything, but this for one asset is for two assets is it's more complicated because then.
Just the one asset.
But one asset, that is what happened. But what I wanted to show is, I mean, this is the kind of, so this is the drift and this is the volatility. So, I mean, what you see, what's the point is that these are very, I mean, they are very nonlinear shapes. I mean, the shaded area is the, so essentially what we do, what you said, but what is that?
Horizontal axis, vertical axis.
Exactly. So what is it? So in the horizontal axis is the dividend. So those are, so here is this object mu k of qy, which is the drift, so the growth rate, if you want to put it like that, of the asset price. Okay. So this is how is the growth rate. So sometimes it's negative, sometimes it's positive. So sometimes here is negative, there is positive, depending on the value of the dividend and depending on the price of the asset. And then what you see is that, I mean, the mean of the dividends is around here. They are autoregressive, so they oscillate in this.
There are regressive.
Yeah, they follow. So dividends are here in this simulation. They follow an AR1, an Ornstein-Uhlenbeck process. Okay.
Okay.
And that is critical because then people know
critical.
that when dividends are low.
You didn't say that, but that's critical.
That's critical for results, because then you know this is why middle class people, because you know that when dividends are low, they will return on average. They will.
But the idiosyncratic interest.
I'm sorry, let me just remind you that 3 minutes over.
Okay.
3 minutes.
Maybe we can postpone further questions.
Okay.
Up to.
So no, I mean, so that was the growth rate, and this is for the volatility. So essentially, it is telling you in which part there is more volatility or less volatility. Something that has surprised us of the basic model. I mean, those are those objects. I mean, this is how. So that is now different. This is how the policy function. So this is the savings policy function for the unemployed. So the two states of the idiosyncratic labor income, and this is how they change the policy function in the stochastic steady state and 1 year after the arrival of a negative dividend shock. But I mean, I don't have time to talk about that. And actually, I just want to. I mean, the whole presentation was a teaser, and I'm glad because if I had tried to present something more, I would have time. So it's better just to come with that. So the point is that. What we have done now is first to extend the model to have two assets, so a bond and I mean, this risky asset and a safe bond. And then the issue is, and this is a big structural decision, is if you just plug the bond with CRR utility and solve the portfolio problem, then you are going to have something that is very nice, but it's totally unrealistic. Yeah. And then if you want to get something realistic, either you start playing with complicated utility functions, or you start adding ad hoc adjustment cost, or you just have to plug. I mean, or that's more or less the trade-off. So we are a little bit. I mean, the issue about considering realistic allocation rules is probably like that, and essentially with that, I mean, the point is what we are trying to do is two things. First, we are trying to see how changes in labor inequality affect asset prices.
Uncertainty.
Then we can analyze also that we haven't thought, but that's a good point. And then there is an important point, which is if the allocation rules, and that's a very important issue, if the allocation rules are not linear anymore, then the quasi-aggregation support of this whole agenda collapses.
Totally.
And then this simple moment probably won't stop. And then there can be other things that can help to predict. So one part of that we want to do is for nonlinear portfolio allocation rules, we want to make a study of which are the key moments of the distribution that help to predict asset prices in the model. Because there is this issue about the wealth inequality can help to predict asset prices or not within the model, not in the real world, within the model. So this is more or less the agenda. I mean, the whole agenda is about solving heterogeneous agents, solving globally nonlinear models, and one example of nonlinear model are these asset pricing models, and we are there. Even if we are using this kind of simple approach compared to the more blowing issues of really dealing. So this just mapping to the prices, and that's, thank you very much.
So do we have any questions from the audience?
So there's lots of empirical literature about how wealth inequality, how asset pricing affecting wealth inequality. But I think to motivate this project, I'm just curious whether there's any empirical evidence that how wealth inequality is affecting asset prices. I know it's extremely hard to identify this.
So then,
I'm not sure whether it's
there is this paper that's when Ricardo knows that there is this guy Gomez, which was your Colombia. Matthew Gomez was a paper about that, about how wealth inequality affects asset prices. I don't know how much because I haven't read it. Had I read it, I would know it. But I've been told, that he has a model. I mean, the modeling part is just a static wealth inequality, so it's not dynamic wealth inequality. You're gonna be rich, and you're gonna be poor forever, but that he should have some legal issues supporting the model, I think.
The wealth inequality needs to arise endogenously within the model.
Exactly, and that's a cool thing. I mean, the cool thing is not to plug wealth inequality exogenously and see
Arising
to have the both ways.
realistic.
So let's stop here, and do you have an announcement to make?
Yeah, not an announcement, but like just a suggestion, like those of you who will come to the conference, that's we will start together at 6:30. The best thing is around this time, just like there is a metro just behind this building. Just take the right side towards long. Then there's a few minutes to walk to the restaurant. So like each restaurant.
Say that again.